Hello, chemistry. Here we are on page 682, section 2 of chapter 18. And we're talking about organic chemistry and particularly hydrocarbons. And hydrocarbons, just by way of reminding, is anything that is made out of just carbon and hydrogen. Carbon and hydrogen. Now, the first vocab word in our section is called a saturated hydrocarbon. What do they mean by that? Well, like a sponge, when it's saturated, cannot take any more water. A molecule is saturated when it cannot bond to any more things. This molecule is saturated. This molecule is unsaturated. Well, how is it unsaturated? It looks like all the bonds are taken. Yes, but each carbon could add another hydrogen to it and become saturated. Now it is a saturated hydrocarbon. Actually, I put chlorine on here, so it's not quite a hydrocarbon, but it is saturated. All the bonds are single, and you can't add anything more to it. I could always undo that process, take off the two hydrogens, put this back together, and now it is unsaturated again. So saturated, all single bonds, and can't add anything more to it. The next thing our chapter talks about is the vocab word alkanes. Now that's pretty simple, except for as we're coming up here later in the section, we're going to have alkenes and alkynes. And we'll teach you what the difference is from each one. But for now, alkanes are saturated hydrocarbons that have just, well, that's redundant, hydrocarbon having carbon and hydrogen only. That's an alkane. Now the first one I'm showing you here is ethane. Ethane has 2 carbons and 6 hydrogens. Now mathematically, what would happen if we add another carbon to it? Well, I would take off this hydrogen and add it here, and now my mathematical totals would be 3 carbons and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So take a look here at our chart, and you'll see that with 1 carbon, we have CH4. Here we have C2H6, C3H3, 6, 7, 8. And here we have C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is there a mathematical pattern that if I know the number of carbons, I could figure out the number of hydrogens? What's the pattern? Well, it turns out that these all are C, and whatever N is, that would be the 1, 2, 3, or 4, 8. So if I take this number and I double it, so I go 2 times whatever N is, in this case 3, and then I add 2 more. That is sort of a generic formula for any hydrocarbon. So if I have 4 carbons, I go put a 4 here, then I go 2 times 4 is 8 plus 2 is 10. So how could I predict what 5 would be? Well, I put 5 in here. 2 times 5 is 10, plus 2 is 12, and so on. So we can predict that if we had a carbon of 100, we would have 2 times 100, 202 hydrogens. And that is conceivably possible. Now, when it comes to molecules, we'll come back to this page in just a moment, but I want you to look at how the naming system works. If we have 1 carbon, the name of that hydrocarbon starts with meth, so that'll be methane. 2, eth, or ethane. 3, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And that's how the naming works, and you need to know how that works. So if we have just 1 carbon, what's its name? Well, it's going to be methane. If it has 2, if it has just 2, then it's going to be ethane. If it has 3, methane, and so if it has 3, it's propane, butane, and so on. Now, I want to show you these without the hydrogens just to try to make it seem a little more simple. So instead of going to the trouble of putting all the hydrogens on here, I'm just going to show it to you like this. So this would be ethane. Of course, just one would be methane. 2 is ethane. 3 is propane. 4 is butane. 5 is pentane. And 6 is hexane. So all of these should have hydrogens on them, but I'm showing them to you this way just so that you can look only at the molecule. So there's hexane. All right, we'll come back to these guys. Now if we go back to this page, when we have just 1, 2, or 3, there is only one option for a way to make the molecule. But once we get to 4, we can arrange it so that we can take one of those hydrogens, pull it off, and stick it on somewhere else, like we did here. And you might remember we called those isomers. So here's 4 in a row, and that is this guy here. But we could easily pull it off of here and stick it onto here and make here 2-methylpropane. And we'll talk about it more as we go along, but you'll notice that butane became propane even though it still has 4 carbons, because we're going to name things based on the longest chain. So in this case, the longest chain is 1, 2, 3. Now, it doesn't matter which way you count. We can go 1, 2, 3 this way or 1, 2, 3 this way. It doesn't really matter. You see it's the same thing, 1, 2, 3 or 1, 2, 3. So we're going to call this propane now because it only has 3 carbons in the longest chain. And then we can attach something to it. Now, what was the name of a single carbon? It was called methane. Well, if it gets attached to something, like this guy is attached, if it gets attached, we don't want to call it methane. So we have to have some little way to say that it's not methane anymore, but it's still 1 carbon. So instead of saying 2-methane propane, they say 2-methyl-propane. Methyl meaning that little group is attached and it lost a hydrogen to bond to the carbon. 2-methylpropane. We'll talk more about that coming up. So as the molecules get bigger with more carbons, there are more and more options. With 4 carbons, there's only 2 options. And as it gets more and more, there are lots, thousands of options. Now remember, whenever something is saturated, it is called an alkane, saturated hydrocarbon. And we've also talked about that carbon has options of being able to do many different things, making chains, making branches, and so forth. And not only can it make chains, but it can bond to itself again and form a complete circle. So we could put a bond here and make it bond in this way. Now, when we said 4, that was called butane. So here is butane. Same things I just had here. I'm going to take off one of these here, and I'm going to have to take off one of these here and put them together, and that is a butane because it's got 4 and it's cyclo and it's saturated. But what would happen to the mathematical formula, because we took off 2 hydrogens to make that work? So now it's C4, but instead of being H10, it's H8. So the mathematical formula for that would just simply be CnH2n. But we can make cyclo just about anything you want. Here's hexane, 1, 2, 3, 4, 5, 6, and we can take it and bond it back to itself. And what's also interesting to note is that it does not stay flat. Not that it was flat, but you can see it's actually kind of a chair shape. See sort of a chair shape there? when we make cyclohexane. And whatever number of carbons, we just call it cyclo. If it's 5, it's pentane. If it was 7, it'd be cycloheptane, and so on. The naming system still works, as you see down here. Now, a little bit about the attached groups. So let's say we have hexane here. Try to straighten it back out. Hexane. And we want to attach something to it. We could attach a single carbon. What is that single carbon called? Well, this is where this chart comes in. One is still meth, but instead of saying methane, we're going to say methyl. What if we attached 2 carbons to the chain? I'm not going to put hydrogens on here anymore. Let's say we have 2 carbons attached here. Well, that becomes ethyl. By itself would be ethane. When it's attached to something, we call it ethyl. That little dash there is to represent this little bond right here to show that it's attached to something. You'll notice over here there's no dash to the left. That would be ethyl. And we can keep on going with longer and longer and longer chains. Now there's one trick to watch out for. It's very tempting to take something like hexane here and say, you know what, I want to add it to the last carbon. Would it be called a methyl group then? No, it would be called 1, 2, 3, 4, 5, 6, 7 heptane. So we can never add a group to the last carbon because that would change excuse me, that would change the length of the chain. Other interesting things happen. I obviously wouldn't put a ethyl group on the end either because that would make it now turn into octane. But what about putting it here? That would still change it because now this becomes the longest chain this way. I cannot add an ethyl group until here because otherwise I'm changing the length of the chain. So watch out for the idea of adding it here. Now, another caution. When drawing, it can be also a little bit tricky. For example, if I were to draw this molecule that is back to our butane. Here's butane. Would that be very different than that? Could that be a methyl propane? And the answer is no, because all we've done is we've really just tried to bend this chain, and it's still 4 in a row, even though we've drawn it this way. So these two are exactly the same thing, and you won't see people do this because this is the most common way we see it. But if you do wind up trying to draw it this way, you need to recognize this is the same as that because they're still connected in the same order, and they are going to want to be this way in this shape because of the Vesper theory. It's also, we're going to illustrate this. If I want to add a methyl group, I could add a methyl group here, and so I'm going to put this guy on here, add that methyl group there. That's legal. But what about if I wanted to add it up here? Is this different than this? No, because all it is I've just flipped this over, and now I've got my molecule this way. So it's the same molecule here or here. These are not different. They're the same thing. Similarly, what if I draw the molecule with the carbon over here? Are these two things different? Well, again, no, because I've just taken this molecule and I've rotated it around to right there. And it is exactly the same thing as if it was right there. So these two are the same. Now I could add more carbons and make something different. These are all different, and they're not isomers because they're different molecular formulas. Our textbook gives us an example of a hydrocarbon that we get to try to name. And it is saturated. There's no double bonds on it. So this is an alkane. And we're going to get to name it. We're going to follow the rules here on page 687. And I've drawn that molecule right here on a piece of paper to take us through the journey. First of all, it says find the longest continuous chain. Well, sometimes that's obvious and sometimes it's not so obvious. Here we have 1, 2, 3, 4, 5, 6, 7, 8 in a row. That looks likely the longest, but it's not always the straight chain that's the longest. There's some other options that are clearly shorter, but we could go 1, 2, 3, 4, 5, 6, 7, 8 this way. It's the same length, so now we've got two choices. Which one do we want to choose? Well, the naming gets easier if we're going to take it this way and down this way because of the branching. So if we went this way, we don't have a way to name this guy, and I'll show you why. So I'm gonna highlight this so we can look at this as the chain that we're going to try to name for our hydrocarbon. So our hydrocarbon's name is going to start out with the longest chain. In this case, it's 8. Well, what name is for 8? You remember the good old octopus. 8 is octa. So let's start by naming this guy octane. Octane. But that doesn't really tell us much because it doesn't tell us anything about what's attached to it, where it's attached, and so forth. So our next goal, it says, oh, by the way, it says to add the ane at the end, which we did. We took the oct and we added ane. So our next goal is to name the alkyl groups. Now, we haven't mentioned yet what an alkyl group is. We've touched on it, but here's the vocab word. An alkyl group are groups of atoms that are formed when one hydrogen of an atom is removed from an alkane molecule. So if we have a molecule that we've taken one hydrogen away and replaced that hydrogen with 1 carbon, 2 carbons, whatever, that is an alkyl group. Because he has the 3, but he's missing 1 of his hydrogens, and so is this guy. That makes him an alkyl group. So our next goal here, according to our rules, is to identify the alkyl groups. The alkyl groups we have are single carbon, and what is that guy called? Methyl. Here's another one. And over here is another methyl. And what is that? Well, that's 2 carbons, and 2 carbons is called eth. So instead of calling ethane, we're going to call it ethyl. So we have 3 methyls and we have 1 ethyl. So it says to name them in alphabetical order. So which one comes first, E or M? E comes first. So I'm gonna leave a lot of space here. We're gonna have ethyl, and then we're going to have methyl. I don't know exactly how much space I'm gonna need here, so for now I'm just gonna leave it with plenty of space. So we've named our 2 groups, and then it says when there's more than 1 branch of the same alkyl group present, we attach the appropriate numerical prefix to the name. 2 is di, 3 is tri, 4 is tetra, and so on. Well, how many methyls do we have? There are 3. So what do I need to put in front of that name? Tri. So we're going to call this trimethyl. Trimethyl. Now with the ethyl, there's only 1, so I don't put monoethyl. It's kind of silly. It's like putting 1x. We just write x. So it's going to be ethyl, not monoethyl. Ethyl, trimethyl. Now these methyls could be anywhere along the chain. So our next rule says number the carbon atoms of the hydrocarbon. If one or more alkyl groups are present, number the carbon atoms in the continuous chain to give the what? The lowest numbers possible in the name. If there are two equivalent lowest positions with two different alkyl groups, give the lowest number to the alkyl group that comes first in the name. This will likely be the alkyl group that first in the alphabetical order, before the prefixes are attached. Okay, so we could name this two different ways. Number this, I should say. We could number it left to right. I'm just used to doing that. 1, 2, 3, 4, 5, 6, 7, 8. So that would be then, we're going to check with two different names here. I'm going to name it two different ways. We're going to still have the octane, we're going to have the methyl, and we're going to have the ethyl, and we're still going to keep the tri. Now we want to name it with the lowest number. So let's start going this way. Here we have 4, so we would name this dash 4, comma 5, comma 7 dash trimethyloctane. And the ethyl would be 6 ethyl 4, 5, 7 trimethyloctane. That's a mouthful. But we could also name it going the other way. We could start with this one as being 1, 2, 3, 4, 5, 6, 7, and 8. It doesn't care if it's upside down, right side up, because things can rotate in space. So we could name it that way. So let's see what our name comes out if we name it the other way. So we would go this way. We'd have 2 methyl. We would have 4. Well, look, there's 4 in both. 4 methyl and 5 trimethyloctane. That's an A. And the ethyl would come out to be a 3. So which of these two names gives a lower set of numbers? The 3-ethyl 2,4,5 or the 6,4,5,7? Clearly, this one gives us the lower numbers, and we will reject this one. If you were to name it this way, someone could figure out what you made, but they might wonder why you named it that way, because we've all agreed on these rules here about the number of for the hydrocarbons and the alkyl groups that are attached to them. This way, someone reading that name could say, oh, I've got an 8-carbon chain, and there's going to be 3 methyls attached at the 2, 4, and 5, and an ethyl at the 3. The last bit of our rules is that we insert position numbers. This is what we did just a moment ago. And we put them in front of the group name, and we punctuate it using hyphens to separate the positions of the number and commas. So that's why we put the hyphens here and the commas to separate the numbers. All right, that concludes this part of section 22.2, and we will continue the next video with the second part.